Hey everyone, here's the video lecture for lecture 5 where we are working with costs here. So we first define costs in the short run sense. So we've already outlined the difference between explicit and implicit costs, and this is something that we went in depth in understanding, and that's creating the idea between accounting and economic costs, and then in turn we're able to calculate economic and accounting profits. So this chapter will help to link the theory of cost with the underlying production technology. And really what this is doing is allowing us to get into then the idea of profit maximization. So for us, in terms of the short run, we start with this total cost function where we have total cost is equal to some generalized function f, which is dependent on Q, where Q is our production level. But in a more general way, we're able to essentially write total costs by including essentially for us this idea of capital and labor, where don't forget that we have capital being fixed. So that's why we have K sub naught. This is going to be some number, right? So we then look, once we've defined total cost in this way, we realize, well, there is kind of a different way that we can understand the total cost. And we essentially here are going to focus on mainly the idea that our capital and labor are dependent upon the prices of both capital and labor. So we assume that these prices, the rental price of capital and the rental price of labor, so we call these the rental prices. So this is rental price of capital, and this is the rental price of labor, which is also just wages. So these are set in a different market for us, and so we assume them to be a number that we're going to be using here. Again, we're assuming that capital is going to be our fixed input, where then labor is going to be our variable input, which makes a big difference for us. So we now have this idea of total cost, which can be looked at in a very general sense with capital and labor. We can also look at then how we are going to include prices of capital and labor. And given that we've assumed that capital is fixed, we now believe that we can rewrite it in a different way, because this is essentially the rental price of capital times that fixed capital, right? And that's our fixed cost, whereas our variable cost now is going to be dependent on Q, which in turn is a function of essentially labor in this sense, just in labor here. So we can move on with this and kind of start defining or understanding a little bit better the short run costs. So total fixed cost, we say that this is associated with acquiring and maintaining factors of fixed factors of production. These costs are incurred regardless of the level of production. Generally, we like to think that they might be binding contracts in some way, rental payments on office space, insurance, legal retainers. Again, anything that you pay for, regardless of what you produce, is going to be a fixed cost, where then total variable costs are associated with acquiring and maintaining variable factors of production. So we talked last chapter about where would that be in terms of the stages of production. So in stages 1 and 2 of production, we assume that total variable cost is an increasing function as a level of output increases. And so generally, we could graph it in this way, something like this, total variable cost. That would work. We could also understand that it could look something like this, total variable cost. So we have two different ways to kind of think about it, where our total fixed cost will look something like this. So we move on then from this analysis to now start thinking about the averages. So for us, this is a very simple idea to grasp, is that the average of fixed cost or variable cost or total cost is going to always be divided by Q. We're going to do some analysis with this, especially comparing the average fixed costs and the average variable cost and the average total cost to then marginal cost. So what does that mean for marginal cost. So we realize that marginal cost is essentially then the change in total cost associated with a change in output. So if we were to look at this again, if we were to look at total cost is equaling total fixed cost plus total variable cost. So if we take the derivative with respect to Q, we know that this will drop out, so that we're really just looking at the change in total variable cost given the change in quantity. So that's what we like to believe is going to happen here, and which will happen actually. Total fixed cost should drop out. So when we see this functionally, so if we were to essentially create a function for ourselves, and we've been seeing this kind of quite frequently, where we have total cost is equal to some number x plus q plus q squared plus q cubed. This is a cubic total cost function where x then, this integer, ends up being our fixed cost for ourselves. So that's how we'll see it in practice. But for right now, marginal cost is going to be that first derivative of our total cost function. So the one thing that we also want to recall, and this will be important later on when we talk about profit maximization, is that our total cost function should be a function of essentially P sub K, P sub L, L, and K. Because once we add in production here, we know that Q is this F of K and L. So we're going to include all of these elements, the production side within the cost side for profit maximization. So that is definitely on the horizon for us. So the one thing that we wanted to make clear and stress is the difference between sunk costs and fixed costs. And so when we think about the sunk costs, they're invariant with respect to changes in any management decision, but they're not exactly the same as fixed cost. So what we like to believe is, I think this is best exemplified through an example, I guess. So suppose we purchase a factory for $1 million. If you make nothing, your fixed cost is $1 million. Now, if you sell the factory, because we have the ability to do so, you have permanently lost $250,000 if you sell the factory for $750,000. This $250,000 then becomes your sunk cost. So essentially the sunk cost is the difference in the purchase price and whatever salvage value that you have. And I think that makes some intuitive sense here. And so we want to make sure that we, if we're reading a word problem in some way, that we recognize that there could be fixed costs and there could be sunk costs. So how do we want to move on with this? Is that we're going to look at fixed costs here, or total costs here in the way that we want. And that is with capital, with labor, with the rental prices of each as well. And so we can now quickly divide by Q to get our averages. So what does this look like for us? What is total cost going to look like? Well, we first recognize that for ourselves, that essentially between 0 to Q1, we can see that total cost is increasing, but it's increasing at a decreasing rate. So it increases at decreasing rate. What does this mean for us? It means that the first derivative of total cost with respect to quantity has to be greater than 0 because it's increasing, but the second derivative has to be less than 0 because it's decreasing, right? And that makes a lot of sense to us. And then at Q1, this is our inflection point. This is where the second derivative changes. So at Q1, the second derivative changes from negative to positive. So that means for us then, that from Q1 on to some Qn in the future, which n is is some limit that we can make essentially. We have the second derivative being greater than 0. Good, and that makes a lot of sense to us when we see this picture. So if we were to start then looking at Q1 and Q2 and what that kind of means to us, we know that the first derivative, so we know that DTC, DQ, is our marginal cost. So how do we interpret then this marginal cost a little bit? Because we know that marginal cost, what is essentially the slope of marginal cost? Well, the slope of marginal cost becomes d marginal cost dq, which is essentially the second derivative of our total cost function. And we know that in the beginning is less than 0, right? So we know that marginal cost is declining up to Q1, and then we know that after Q1, dt dq, that the slope of marginal cost is greater than 0. So essentially we're creating at this inflection point of Q1, we're saying that marginal cost has reached some sort of minimum point there. Good. So now how do we interpret then kind of this Q2 point? Again, Q2 is going to tell us that essentially that we are going to, in essence, are going to be finding some minimum average total cost. How do we know that's the minimum in some way? Because at this ray through the origin, as we essentially, so if we draw something out, let's draw it out like this. So if we have a ray through the origin, and we keep connecting dots like this, we keep going, what we're going to find is that the slope is declining with the red until we get to this point at Q2. Then as we start connecting more dots, the slope now is getting steeper and steeper. So the slope originally declines with the red and then gets steeper and steeper with the green. So that means in terms of the average cost, that if we were to draw this, that we would see that average total cost would be going down, and then at Q2, essentially, we would reach our minimum point. So why does total cost look this way? We want to understand it, and in the short run, essentially what we're realizing here is that if we take the first derivative, in this essence, what we end up getting is that it's dependent upon this marginal product of labor. So we see that the shape of the total cost curve is specifically connected to this marginal product of labor. It's very important that we recognize this, because as we compare to the long run, we're going to see that that's not necessarily the case. So this is an important graph for us. What it does is show the relationship of the average variable, average fixed, and average total costs with marginal costs. And we know the shape of these cost functions, and that is due to this law of diminishing marginal returns to product. And I think that's extremely important. The reason that we're seeing at first between average variable cost, average total cost, and marginal cost that they're declining is the idea that we have some increasing marginal product. And again, I think that's an important idea, that we get this U shape in these curves because of the increasing then diminishing marginal product for ourselves. But what we notice here is that if we were to draw this out, essentially that marginal cost hits average total cost and average variable cost at their minimum points, min of each. So I think that's important. We're going to go mathematically through why that is, but let's keep this in the back of our mind as we move forward, maybe with a problem here. So this is something that we went through in class. So this is in the book, problem 6.1. For most of his professional career, David Ricardo was a computer programmer for IMC. During his last year at IMC, David earned an annual salary of $120,000. So I think that might be important. Last year, David founded his own consulting firm, Computer Compatriots. His monthly fixed costs, including rent, property, and casualty insurance. So we have fixed costs totaled $5,000. So we now essentially can look to, so we have fixed cost equaling 5,000. David's monthly variable costs, including wages and salaries, telecommunications service, personal computing, and maintenance, amounted to 20,000. So I think that was important. So we have essentially personal computing. Oops, let's do this again. So we have personal computing. Variable cost. All of this $20,000. Good. So we have variable cost 20,000. So we have some things that are popping out to us. Assuming that David does not pay himself a salary, what are the total monthly explicit costs of Computer Compatriots? Well, this is easy, right? This is the money that's going out for ourselves. And so we have the sum of the two together. So we should have total costs being 20,000 plus 5,000. And so when we now look to part B, what are the firm's totally monthly economic costs? What kind of pops out here is the idea that for the year, David was making $120,000. So for every month, David makes essentially $10,000. So now we want to add that in so that his essentially economic costs are the total costs explicit plus the total cost implicit. And this is our economic costs. So we have 25,000 plus 10,000, and we get then 35,000. Good. So now as we kind of move on, we're going to look at a more generalized notion of our total cost function. Like I said, we're looking at maybe a cubic function. That doesn't always have to be cubic. We can see just the second derivative. We could see just the quadratic equation. And that would work too for our total cost function. But we would expect total cost then, again, if we think this is cubic, then this would have to be essentially quadratic. Okay, so we notice that with the quadratic formula, so if we were to kind of if we were getting rid of this element here, we would realize that this quadratic is important. It tells us then that there's no increasing returns to product, marginal product, where the cubic function has this area for ourselves. So we have this area with the cubic where we have increasing and a decreasing rate, which tells us that we have some sort of increasing marginal product. So how do we know some of the values, and how do we interpret some of the coefficients, beta naught, beta 1, beta 2, beta 3? Well, for us, what we're going to expect here is that beta naught is our fixed cost. So it makes sense that beta naught be greater than 0, because it doesn't really intuitively make sense that beta naught would be negative. So as we move on then to beta 1, beta 2, beta 3, this something becomes really interesting here, is that in order for us in this cubic function to get beta 2, to get the increasing marginal product, what we essentially have to do is make sure to get this shape that beta 2 is less than 0, where beta 3 would then be greater than 0. So to get this shape that we're looking for, this is the intuition that we're providing. But we have a separate condition here, that 3 beta 3 times beta 1 has to be greater than beta 2 squared, which all has to be then greater than 0. We know why that is. Beta 2 squared should be greater than 0. If we believe it's negative, the square of a negative is a positive. And if we believe beta 1 is positive, and beta 3 has to be positive in order to get this upward sloping shape, it makes sense why that also is greater than 0. And so we had a problem in our notes to essentially solve for this. I'm sorry, in our homework to solve for this. And I think it's a good exercise to go through on your own to kind of refresh your algebra and to understand how it is that we're solving for these values. So following along though, if you wanted to solve this, what we would do is first is essentially find the first derivative with respect to our total cost curve. So if we were to do that, we have total cost is equal to beta naught plus beta 1q plus beta 2q squared plus beta 3q cubed. So then we want dTc dq. So recall, beta naught is going to fall out. This is our fixed cost, so beta naught goes away. It's not dependent on q at all. So then we are left with beta 1 plus 2 beta 2 times q plus 3 beta 3 q squared. Good. So now essentially this is our marginal cost. So we've taken our first derivative. We have marginal cost here essentially. Now we want to take the first derivative of marginal cost, which is essentially that second derivative of total cost, and what we're going to do is set it equal to 0. So we're going to do d second derivative dtc, second derivative with respect to q. Again, now beta, essentially beta 1 is going to drop out for us. So we're left with 2 beta 2 plus 6 beta 3 q, which is going to be then equal to 0. So essentially this is going to be, this solves for minimum marginal cost. So this q will get us that minimum marginal cost. So how do we do that? Let's go to 2 beta 2 is equal to negative 6 beta 3 q. So that negative 2 beta 2 over 6 beta 3 is equal to q, where we have negative beta 2 over 3 beta 3 is equal to q. Again, where we're solving for the minimum. And this makes sense if we were to find this, this q should be positive, because we've assumed that beta 2 has to be negative. So we now can essentially substitute this optimal, this minimizing value back into our marginal cost to look a little bit further. So we're going to look at beta 1 plus 2 beta 2 times negative beta 2 over 3 beta 3 plus 3 beta 3, and then we have q squared, so negative beta 2 over 3 beta 3 squared. This is our marginal cost. So we want to know what marginal cost is at the minimum point, and it should be less than anything else. So we can kind of solve down a little bit. Beta 1 plus negative 2 beta 2 squared over 3 beta 3 plus 3 beta 3 times negative beta 2 squared over 9 beta 3 squared. Again, we can simplify here so that we have beta 1 plus negative 2 beta 2 squared over 3 beta 3 plus negative beta 2 squared over 3 beta 3. And what we want to do is say that we want marginal cost to be positive, greater than 0 in some way. And if we do that, we can now kind of rearrange what's happening here. I'm sorry, we need to make a correction, sorry. So we are going to have a positive here. So this is positive, this is positive. Okay, so what we now want to do is with this is we can set beta 1 plus beta 2 over 3 beta 3 equal to each other. The reason we're doing this is because we have, from this relationship, we should have negative 1/3 beta 2 squared over beta 3. So we can set that equal to, essentially, beta 2 squared over 3 beta 3. So now we can say that 3 beta 1, this would be greater than, is greater than beta 2 in order for this to be greater than 0, which both of these are greater than 0, and that's exactly what the condition we suggested to have in the beginning. So if we wanted to have just diminishing marginal product, here we would suspect that beta 1 would be positive, beta naught would be positive again. So we have this firm's total cost function. We can calculate out some things. So suppose a firm produces 10 units of output, calculate total fixed cost, total variable cost, average total cost, average fixed cost, average variable cost, and marginal cost. And the way we do that, total fixed cost is going to be 12. Regardless of what we do, we plug in 10 here, doesn't matter. We know that 12 is going to be essentially this fixed number for ourselves. So that's our fixed cost. Then the average fixed cost is going to be, if fixed cost is equal to 12, and total cost at 10 units is equal to 12 plus 60 times 10 minus 15 times 10 squared plus 10 cubed. What we could do here is look at, to get total variable cost at 10 units, we can take total cost at 10 units minus 12. And that'll get us our total variable cost. The way that we're going to get the averages is then take our total cost at 10 units, divide it through by 10. That's our quantity. Then we can get the total variable cost at 10 units, divide it through by 10. So this is average total cost at 10 units. This is average variable cost at 10 units. And the way we could do our marginal cost and then calculate it at 10 units is that we need the first derivative at 10 given dq. Okay, and so this will give us all the information that we need, and we can solve down through here to get the solution. So the last little bit that we want to recognize is that there again is a link between the marginal and the average cost. If we define average total cost to be total cost divided by Q and take the first derivative, what we end up realizing is that when we set it equal to 0, that the minimum average total cost will equal marginal cost. And we can do the same analysis for variable cost as well, and I actually urge you to do that. So how do we know that this will be true? And what else do we know? We can perform this exercise to look at average variable cost. And what we do know is that marginal cost will intersect both average variable cost and average total cost from below. And that makes sense. It means that in the beginning, marginal cost should be less than average total cost. And that average total cost is declining because marginal cost is below average total cost. And when average total cost is rising, marginal cost must be above average total cost. And that's for the intuitive reasons that we've discussed at length in class. So here's a problem that we can solve. Suppose that the total cost function of a firm is given as TC is equal to 1,000 plus 10Q squared. So determine out of this the minimizing average total cost. So we can start with total cost is equal to 1,000 plus 10Q squared. So that average total cost is going to equal to 1,000 Q plus 10Q. So we want to look at what output level minimizes average total cost. So let's do the first derivative with respect to Q. So we get negative 1,000 over Q squared plus 10. That should be equal to 0. So let's solve some things out here so that we get 10 is equal to 1,000 over q squared. So that we have 10q squared is equal to 1,000. So q squared is equal to 1,000 divided by 10. So we get q squared is equal to 100. So the square root of 100 is 10. So this is our quantity that minimizes our average total cost. So at this output level, what is total cost, average total cost, and marginal cost? So what we could do here is take this value, and we should be able to plug in these values. So at total cost, at 10 is equal to 1,000 plus 10 times 10 squared. So then average total cost at 10 is equal to 1,000 divided by 10 plus 10 divided by 10, 10 times 10. So then we get marginal cost at 10. Well, we haven't solved for the marginal cost yet, but we can solve, and that's going to be 20q. And so 20 at marginal cost at 10 makes a lot of sense here, especially when we solve for average total cost. So we know that this is 200. Well, at average total cost should equal marginal cost at the minimum, so we know that this will be 200 as well. So verify that the output level marginal cost is equal to average total cost. That's true, we've already done that. And that the average total cost intersects marginal cost from below. Well, what we could do here is take a different value. Let's look at marginal cost, let's look at a quantity equal to 5. And we could see the relationship between average total cost and marginal cost at this level. We would expect that average total cost should be essentially greater than the marginal cost at an output level of 5, right? And that makes sense graphically for us. Or is marginal cost and average total cost. So that at 10, right, so this was 200 at 10 units. And so at 5, we could see that marginal cost should be less than our average total cost. And so this kind of goes into the diagramming in part C. So determine the output level that minimizes average variable cost. So now what we would want to do here is look at our total variable cost, and that is just 10q squared. So we could look at dTVC over dq is equal to 20q. So essentially, from here, we could go on to solve for marginal cost, set that equal to marginal cost, and actually solve it out. And so we have the answers and the solutions out through here that you could follow along with. So we can look then at diagrammatically what's happening here, and exactly what we would expect to occur is going on. So this was the very first part of the cost curve lecture. And so what we did next is change gears a little bit to look at the long run. But before we looked at the long run, what we wanted to do is discuss this new idea called the learning curve. And so the learning curve for us was important. So up to this point, we've assumed that each additional labor unit has been identical. That assumption doesn't seem to hold in the real world, though. Think about a job that you've had where you started on the very first day. It's almost surely you were better on the last day of your work than you were on the first day of your work, but nothing changed. You were the same labor unit. So how do we account for something like that? So let's assume now that typical labor input gets better and workers get better as they gain experience. So at this point, what we want to do is look and compare your output level versus your cost, because although your wage rate might have stayed the same, you're now able to produce more units with the same number of inputs that you have. So why does this actually happen? Well, one is because you're just repeating the same job over and over again. Another reason is that you could get employee training, or you could have continued education in some way. So we're cultivating some way your human capital, and there's a variety of ways to do this. So the relationship between increased per worker productivity and reduced per worker cost at fixed labor prices associated with an increase in output and experience is the learning curve effect. So this big definition says that we have a learning curve effect. And so we can see that we're taking into account a few different things here. Right? So for us, what we're concerned with is we want to look at the relationship between increased per worker productivity, right? You get better and better with time, and the reduced per worker cost. Again, that's important. And what we're saying here is that we are going to fix the labor prices. So you're not getting raised through this time. You're just getting better. So how can we measure this mathematically? Well, we have this formula for ourselves. So we now create this new formula that's going to look at the learning curve effect. So phi is the per unit cost of producing the first unit of output. This is going to be a number. This is a parameter of value that you're given. Q is some level of output we're concerned with. So we're going to see that we're going to look at the relationship of you producing 1 unit to maybe 50 units to 100 units, where then beta becomes the important factor here. Beta is the ratio of the log learning factor to the log of output proportionality. So if we go in a little bit more depth, what does this ratio look like to us? Well, again, we're going to give you these values. I'm going to tell you what M is, and I'm going to tell you what lambda is. So M essentially is the rate at which workers learn, and it'll take a value between 0 and 1, and can include 0 and 1 as well, where this lambda value is also going to be given to you. And essentially, it's just this proportion value that we're going to induce. So how do we look at this essentially? So as the value of the learning effect approaches 0, the learning curve effect, so the value of the learning effect approaches 0. This is this M. So as M goes down, the learning curve effect on lowering per unit labor cost becomes more powerful. So as M goes down, per unit labor costs go down as well. And that's important. So that's an interesting observation that we can make. And we can see how this kind of takes into effect. So we have 3 different columns here. And in this, we have essentially 3 different M values. Again, remember, as M goes down, that leads to per unit costs going down as well. And so as we, again, go down from 9 to 8 and 8 to 7, we see that we are going to decrease per unit labor costs quicker. So now we're concerned, look at the 256th unit of output that we've made, is our labor, because of learning, the cost per unit of production has gone down. Right? You're able to produce things faster. You just can do it better because of this learning effect. And as that learning effect is stronger, and stronger we mean going down in a sense, we have per unit labor cost going down even faster. And then as we have an M of 0.7, we have per unit labor cost going down even farther. So again, think of this is that, I guess a good example is, imagine you're a cashier at let's say at a local video store. And at your video store, on the very first day, you have a whole slew of options that can happen. You can, during different days of the week, you have different prices. So between Monday, Wednesday, and Friday, you're charging lower prices than you would Saturdays and Sundays, and Tuesdays and Thursdays are even lower because no one rents videos there. And you're trying to remember all the different prices, and you have a line of customers. And some of the customers are going to be renewing memberships and getting new memberships, and they're new customers, and they're looking for videos. And that very first day, you might feel overwhelmed, and it will take you a very long time to get through this line of customers. But you're still getting paid the same amount, right? And so to the video store, you're really unproductive because they're paying you $15 an hour or $10 an hour, and you're not really producing much. You're not helping very many people. But now you're there a year, right, or 256 days. so to speak. And so you're there 256 days. And so after this 256th day, you have the same line of customers. But now you've been doing it day in and day out, and you realize, well, I can accomplish a lot of things really quickly. And I think that's really good. A really good understanding is that now you have learned the process and you can understand how to check customers out of line very quickly. And that's exactly what this learning curve is taking into account. Nothing's changed with your labor. You're not really better or worse or anything. So how can we solve a problem with this? Suppose that the labor cost of a firm of producing a single unit of output is $5,000. If the learning factor is 0.74, so this is M, and the factor of proportionality is 2.5, estimate the per unit labor cost of producing 120 units of output. Then I want you to think about, if the wage rate is constant at $15 per hour, how many labor hours are required to produce the first unit of output? And then how many labor hours are required per unit of output when 120 units of labor are produced? So the next step essentially here is to then look at plugging things in. So for us, now what we're going to do is look at the per unit labor cost, and that's going to be this gamma factor. Gamma is equal to phi. Phi was, for us, was 5,000, so we plug in 5,000. We're looking at the 120th unit of output, so that's Q. And then we create this ratio. We have Q to the beta, where beta is the natural log of 0.74 divided by the natural log of 2.5. Crunch these numbers out in a calculator, and you get a per unit cost of 1,037. So at the very first unit you produced, it cost you $5,000 to produce that unit, whereas your 120th unit, because your labor is able to learn, it only cost you $1,037 per unit. That's very important. So now we go to part B. The first unit we know is going to require $5,000 essentially dollars to produce that first unit. And at $15 an hour, that means that it took you 333.33 labor hours to produce that first unit. But now for that 120th unit, we know that it'll cost you $1,037. We've just calculated that in part A. And at a constant wage rate of $15 per hour, it means that you were able to cut down the labor used to 69.13 labor hours. That's impressive. That's amazing, actually. So we switch gears one more time to start talking about long-run costs. So long-run costs for us are the point at which all factors of production are assumed to be variable. So if that is true, then there is going to be no fixed cost. What we have to realize then is that in the long run, there's no equivalent of the law of diminishing marginal product. It just doesn't work that way. So we have to create a new reason or new idea as to why long-run costs are going to be shaped the way they are. We're going to notice that in the short run, the long-run production function and the cost function are really similar to the short run and the long run. So we're going to begin by developing this production function. So if we say that we're going to scale our operations up, right? So we're talking about the size of essentially our firm and how much then we can produce. So that's why we have Q on the vertical axis. Q on the vertical axis means how much we can actually produce given the size of our firm. So in the beginning, right away, between 0 and this point, essentially x1, between 0 and x1, we realize that we have increasing returns to scale. So our scale of operations is really small, but we realize that we can have increasing returns. And so that gives us a kind of a unique shape here, is that long-run total product is increasing at an increasing rate. Where constant returns to scale takes over, we see that this is linear. This is like a straight line. Imagine this is a straight line. And so this goes all the way up to x2. So between x1 and x2, we have constant returns to scale. So it doesn't matter, essentially, we can produce more, essentially, but we have to scale up our resources by the same amount. Whereas then after x2, we have decreasing returns to scale. where long-run total product is now increasing but at a decreasing rate. And eventually we might see some sort of coming down of this long-run total product. So the shape of the long-run total product is developed using this intuitive approach. So we think that in this increasing returns to scale component, we have firms in the short run, the small scalable firm, we see that they're able to specialize both in human and non-human inputs. So some of the human inputs that they're able to specialize in is saying things like, well, let's have an in-house lawyer. Let's have someone dedicated to taking over all of the law responsibilities. Whereas we could also have dedicated accountants and economists who are going to just look at those factors, and that frees up resources to do other things. One of the ways that a non-human input can essentially be productive is that generally, and this is an anecdotal evidence, but this works in a lot of contexts. If we have to create electric utility or generation, it makes a lot of sense to make a bigger piece of equipment that has larger capacity. Overall, this may be more efficient than by creating a machine of maybe smaller capacity. And that's the idea that we want to take here. So why do we have decreasing returns to scale? Well, here we think that firms get larger once that scalable operation goes up. And there's inefficiencies that occur because essentially we've exhausted all of the efficiencies from being a smaller scale company. So we have things like increase in administrative layers, more bureaucracy, internal politics, more shirking, internal coordination problems. All of these things lead to this idea of diminishing returns to scale. So how do we then equate this to the cost function? Well, our cost function looks very similar in the long run as it did in the short run. But again, the reason why we're seeing this is because we have increasing, constant, and decreasing returns to scale. Here, we start at the origin because we essentially know that there's no fixed cost. No fixed cost means we start at the origin. And we have the same increasing returns to scale, constant returns, and decreasing returns to scale that we saw in the production because we know the link already between production and costs. So how do we relate these into terms for the average total cost function? So scale, we've discussed this. This is refers to size. So does the size of a firm's operation affect its per unit cost of production? I would think, yeah, absolutely. We're going to see this occur. So economies of scale says if we assume constant factor prices, while the firm's total cost of production rises proportionately with an increase in total factor usage, per unit cost of production falls because output has increased more than proportionally. Again, the idea, this says that on average, our long run average total costs fall because we get more return from our scalable inputs. That's exactly what we would think would occur because of increasing returns to scale. And so we use this definition and this idea to kind of look at this diseconomies of scale in the same way. So diseconomies of scale relates to us that per unit costs of production essentially is going to rise, and therefore long run average total cost will rise as well. So we want to think here decreasing returns to scale. And when there's no change in our cost function, that's due to the essentially and the average cost function. That's due to there's no change in essentially the proportionality between output and inputs. So that is our constant returns to scale measurement right there. So how do we then build this long run average total cost curve if we know what it's going to look like to some degree? So as firms plan for the long run, they assume that different scalable options can be made for fixed capital inputs. So we can scale our firm to be really small to really large. And so we're going to create several different plans. And these plans are going to be dependent upon what we believe future demand will be, future supply is going to be. So we take in all of these future expectations and create these short-run ideas, which we are then going to use as a blueprint for essentially the long run. And regardless of what happens here, firms will always want to minimize per unit costs. Always, always, always. So that's going to tell us something else. So what results is from all of these short-run average total costs is we create this long-run average total cost curve. And what we say is that it's going to envelop these short-run average total cost curves by identifying the minimum points of these short-run average total cost curves. And these minimums essentially make every point on the long-run average total cost curve. And so what we have here are these minimums, and you're going to have to believe that this is true, but we have these essentially minimum points that are tangential here. So we have tangent, 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 tangential, right? Something like that, tangential. And these are all the minimum points that we're looking at. And essentially what then we create out of this, and there'd be many more of them, is this long-run average total cost curve. So this would be something where we have small fixed cost. So we have low fixed cost here, where then over here we would have higher fixed cost, right? And that's because we're scaling up. We know that Q is directly related to that scalable idea. So if we have high fixed cost here, this means that we want to be bigger, we want to scale up in the long run, we want to be a big firm. And so the very minimum point, this Q star, this refers to something special. This is the MES. So we say that this MES is essentially just the minimum. It's the long-run average total cost minimum. And so we know how to solve for that now. We're really good now at solving for minimums. So we can do that. So for us, before we get to a problem, we want to just acknowledge that there's actually no reason, we call it a priori reason, that the long-run average total cost has to be U-shaped. It could absolutely be different shapes, and it's always going to be shaped by industry characteristics here. So we talked about things. This might be a shape that's very reminiscent of an industry that has a natural monopoly. And the reason for something like this, the reason that we have maybe a natural monopoly in this situation is that this firm, as they scale up, the long-run average total cost is going down. And for them, they want to have that. We want to have one firm in this industry because we're going to have extremely high fixed costs here. And so if this firm is going to create high fixed costs, if this firm's going to produce and has high fixed costs, they want to be able to sell to as many people as possible. And so we have reasons for the second and third panels as well that we won't necessarily get into. We might get into it later on in the semester. But let's solve a problem. So the firm's long-run total cost curve is given by this expression. So what is the firm's long-run average cost equation? We just want to know the long-run average cost equation. So average long-run total cost is going to be 2,000 divided by Q minus 5Q squared divided by Q plus 0.005 Q cubed divided by Q, so that we get 2,000 minus 5Q plus 0.005 Q squared. Now, what is a firm's minimum efficiency scale of production? Well, let's take the derivative of the average long-run total cost curve with respect to Q, so that we essentially get negative 5 plus 0.01 times Q, set that equal to 0. So then we can solve. So we have Q, 0.01. Q is equal to 5. So Q is equal to 5 divided by 0.01. And so we can see that our answer is indeed 500. So we have Q. So we have Q is equal to 500. So the minimum efficiency scale of production is 500. Very easy problem to solve here. So the next bit that we want to talk about is essentially looking at different levels of output or different combinations of output. So what we have here is something called a multi-product cost function. And it seems only natural to allow a firm to produce goods Q1 and good Q2. This is like having Ford making cars and trucks, Dow Chemicals making different chemicals in their plant. You have Kellogg making different cereals. And so we restrict our production and our cost functions to be limited to just one input to make things very easy. Well, we realize that creating a second output doesn't complicate things that much. So what we want to assume, though, is that firms use the same production facilities to produce two or more products, and they use the same inputs to do that as well. So how can we look at this? Well, we can look at the multi-product cost function in two ways. Is there economies of scope, and is there cost complementarities? What does that mean? So economies of scope essentially says, do we need to, or would we want to double the factors of production to produce goods? Right? Do we need cooks just to make pasta rather than meat dishes? The answer should be no in some way. So the total cost of using the same production facilities to produce two or more goods has to be less than the cost of producing these goods exclusively. So economies of scope in production exist when the total cost of producing two or more goods is lower than essentially producing each one separately. So what we're saying here is this is the total cost of just producing Q1, and this is the total cost of just producing Q2, right? And so the combined total cost is going to be greater than if we were to produce together Q1 and Q2. So we can measure that in some way, and it's not too bad to do mathematically. And we have cost complementarities. Now this means for us that the marginal cost of producing good one is reduced by increasing the production of the other good. Okay, so how do we do this? First, we need to find the marginal cost of producing good one. So MC1 is going to be the partial of total cost with respect to the partial of Q1. But now, in order to observe these, what we do is, what we have to look at is what we call this cross-second partial derivative. So really, what we're doing is taking the derivative of our marginal cost function with respect to the alternative Q. So here we have this to be a very generalized scenario. In our first example, we had MC1 of Q1, Q2 is equal to DTC dQ1. Really, we want to take the second derivative now with respect to Q2. So we have the second partial of TC with the first partial of Q1 given the second partial of Q2. That's exactly what this cross price is. If this is negative, if this is less than 0, then we observe cost complementarities. Okay, so essentially this means that with our marginal cost, as we change Q2, as we increase the amount of Q2, did our marginal cost change? Did it go down? And if it went down, then we have cost complementarities. So what are things? We talked about these a little bit. This is creating beef and leather. This is creating donuts and donut holes. This is creating wine and grappa. These are the cost complementarities that we want to speak of. So in a problem that we have here, we have total cost is 100 minus Q1 times Q2 plus Q1 squared plus Q2 squared. So we have total cost is equaling 100 minus Q1 times Q2 plus Q1 squared plus Q2 squared. So we have goods Q1 and goods Q2. So if the firm produces 2 units of good 1 and 4 units of good 2, do cost complementarities exist? So how do we do that? So we have total cost, and we have Q1 and Q2. So let's say if we want to look at cost complementarities, we want to see what is the total cost when we actually produce 2 units of good 1 and no units of good 2. We want to know then what is the cost when we produce no units of good 1 and 4 units of good 2. And then we want to know the total cost when we produce both 2 units of good 1 and 4 units of good 2. So in order to do that, we just plug in values. So we have 100 minus 2 times 0 plus 2 squared plus 0 squared. So we should get 100 plus 4, which is 104. And then we have 100 minus 0 times 4 plus 0 squared plus 4 squared. So we should get here 116. And now if we plug in both values, we get 100 minus 2 times 4 plus 2 squared plus 4 squared. And this gives us 100 minus 8 plus 4 plus 16, so that we get 112. So the total cost of producing 2 units of good 1 and nothing of good 2 and nothing of good 1 and 4 units of good 2 is surely greater than the total cost of producing both goods 2 and 4 in the same production process. So we have essentially, we found that cost complementarities do exist. Cost comps do exist here. Good. And so for part B then, do economies of scope exist for this firm? I'm sorry. So we just did the economies of scope. Do cost, so here we go. Sorry about that. This is the economies of scope. Do exist. Cost complementarities now. For us, what we're going to do is look at the first derivative of each. So we look at DTC dQ1. That's going to be equal to minus Q2 plus 2Q1. Now you should ask yourself here, well, does it matter what I start with? Could I have started with Q2 and then taken the derivative with respect to Q1? Or do I have to take dQ1 and then dQ2? It doesn't matter. We have a theorem called Young's theorem in calculus that says it won't matter how you start. We will get to the same result. So here we're going to do now the second derivative with respect to Q2. And so we get negative 1. And so we have this less than 0. So yes, indeed, we have cost complementarities existing. Do exist. Good. So that is A and B. How will the firm's total cost of production be affected if it decides to discontinue the production of good 2? So clearly the firm's cost, right, if they were to do that, the cost would essentially decline by the cost of making good 2, which was what we found to be essentially 104. So if the firm discontinues production of good 2. So we essentially get, so we have 112 minus essentially 104, which gives us essentially 8, and that's how we would solve that answer out. So this is it for the cost lectures 5 and 5B, and we'll be back after this week on talking a little bit more about profit and profit maximization.